In this session, we're going to look at a geometric interpretation defining the distance an object travels from the velocity versus time graph. So we're going to begin by looking at the velocity versus time graph for an object traveling with constant velocity. Now the geometric interpretation of this is that the area underneath this velocity curve, which in this case is a nice pink line, and the time axis is going to be equal to the distance the object travels. So let's start to develop this idea. So in this case, the area underneath the curve is going to be equal to the change in distance, which I'll represent as delta x. In this case, we'll look at one-dimensional motion. Now, the geometric object being traced out is going to be a rectangle. Now, rectangles have an area of the height of a rectangle times the length of the rectangle. And in this particular case, the height of the rectangle is represented by the velocity, and the length of the rectangle is represented by the change in the velocity. So I can rewrite the height times the length as the velocity times the change in time, and that's going to equal the change in distance. Now this is true for an object moving with constant velocity. An object moving with constant velocity travels equal distances in equal times. And sometimes you've probably seen this in a math class as the equation distance equals velocity times time. Now this is only valid when the velocity is constant. Now one last thing to point out about this equation before we move on to the geometric interpretation of an object traveling with uniform acceleration. Now if I take this same equation, velocity times the change in time equals the change in distance, if I divide both sides by delta t, what you do to one side of an equation you have to do to another. Notice that this term cancels out with this term. In the equation that I'm left with is velocity equals the change in distance per change in time, which just goes back to the definition of what velocity is, a change in distance per change in time. And this, again, is only valid for an object moving with constant velocity. Now what I'd like to do is take a look at the velocity versus time graph for an object traveling with constant acceleration. Now for an object traveling with constant acceleration, notice that the area swept out by the velocity curve, in this case this nice linear line, is not the same as a rectangle. So in this case the area underneath this curve is equal to the area of a triangle. So let's take a look at that. So the area swept out by the velocity curve for an object traveling with constant acceleration is going to be equal to the area of a triangle, which is 1/2 the height of the triangle times the length of the triangle. Now if we look at the velocity versus time graph for an object traveling with constant acceleration, notice that the height of the triangle is going to be the change in the velocity, v final minus v initial. And the length of the triangle is going to be t final minus t initial. And so now we can rewrite the area of this triangle as 1/2 the height, which we said was the change in the velocity, times the length of the triangle, which is the change in time, which this works out to be 1/2 v final minus v initial times the change in time, delta t. Now I'm going to use a little math trick to manipulate this equation and put it in a form that's easily recognizable. So I'm going to multiply this equation by the number 1. Now notice that in this case this number 1 looks kind of weird. I'm multiplying this by delta t over delta t, which is really equal to the number 1. So I haven't actually changed this equation. I haven't done any weird math on it. All I'm doing is multiplying it by the number 1. Now when I do that, notice that I can now rewrite this as 1/2 v final minus v initial times time, or the delta t squared, divided by delta t. Now I'm going to manipulate this just a little bit. So what I'm now going to do is I'm going to rewrite this as 1/2 v final minus v initial times delta t quantity squared. And notice what I'm going to do is I'm just going to bring this right underneath this term here and write it as delta t. Now what you should see is that this term right here, which I'll write in parentheses now, is equal to the acceleration of the object, how fast the object's velocity is changing per unit of time. So now I can rewrite this whole equation as 1/2 times the acceleration times the time to change that velocity. And this is going to again be equal to the distance that this object travels. Now notice that this equation is much different than the equation that tells us the distance an object travels if it's moving with constant velocity. So notice this is the distance for an object traveling with constant acceleration from rest. And this is the equation for an object traveling with constant velocity. Now the equation that we just discovered that tells us the distance an object travels when it's traveling with constant acceleration was 1/2 acceleration times the change in time squared. Now this equation holds true if the initial velocity is 0, but if we were to look at another graph, another velocity versus time graph, in which the object does not start from rest, but instead starts from some initial velocity, so if this is our initial velocity, and it starts with something other than 0, notice that in this case, we assume that the initial velocity was 0, but that's not always the case. So we're going to assume a non-zero initial velocity here. And what we're going to do for this final case is just look at what the distance this object would travel if it had some initial velocity other than 0. And again, this is a velocity versus time curve for an object traveling with constant acceleration. Now in this case, the area under this curve is equal to two areas. In one case, it's equal to the area of a triangle, and in the other case it's equal to the area of a rectangle. The height of the triangle can be represented by v final minus v initial, and the height of the rectangle can be represented by v initial. Now to find out the distance this object travels, all we need to do is find the area underneath this curve, which in this case, the area, which I'll represent is going to be our displacement, our distance, is going to be the area underneath the curve, which in this case is going to be the area of a triangle plus the area of a rectangle. Now in this case, the area of a triangle, you know, is 1/2 the height of the triangle times the length of the triangle, plus the area of a rectangle, which is going to be the height of the rectangle times the length. Now in the case of the triangle, now the height of the triangle is v final minus v initial, and the length is going to be our change in time. So we can go back down to our equation, and now we can write this as 1/2 the height of the triangle, which is v final minus v initial, and the length in this case is going to be delta t, plus the height of the rectangle, which in this case we said was just the initial velocity, and the length is going to be the change in time. And so now we can now write this as v initial times delta t. Now if you go back to the relationship we just derived, we said that this term right here is equal to 1/2 the acceleration times the change in time squared plus the initial velocity times time. And to summarize, that just equals our change in distance. And this is our relationship for the distance an object travels while it's accelerating. Now the one last thing about this equation before we move on is that constant velocity is a special case of this general equation here. So if I just rewrite this as delta x equals v initial times time plus 1/2 acceleration times time squared, which is the form you often see it in. If the acceleration is 0, that is, if this term is 0, this entire term here is going to be 0. And so you're left with delta x equals v initial times time. And this would tell you the distance an object travels while it's moving with constant velocity, that is, when it's not accelerating.